The city of Vienna, living space for 1.6 million persons. Austrian capital, administrative centre, location of large enterprises and international organizations, university town, metropolis. The quality of life here depends entirely on a smooth-running supply and waste disposal system.
More than 900,000 dwelling units have to be heated. More than 450,000 tons of household waste have to be disposed of every year.
In the city, there is a concentration of people and problems. This is, at the same time, a chance for intelligent connections and economical networks. Fernwärme Wien has seized the opportunity.
9 plants operate on a combined basis and by means of a 700-kilometre-long network supply 150,000 dwelling units and more than 3,000 corporate customers with heat.
Almost 1/5 of the energy is derived from the incineration of waste, a considerable part from the utilization of residual energy from generation of current from thermal power compounds.
The Spittelau district heating plant is one of the most important units in the district heating network. It is the most powerful waste incineration plant in the district heating network, as well as being Austria's largest producer of district heating.
Spittelau is, in fact, 2 plants in one, a waste incineration plant and a district heating plant.
The plant is able to supply the Austrian network with altogether 460 megawatt of heat. In the 2 waste incineration plants, Spittelau and Flötzersteig, more than 450,000 tons of household refuse are disposed of thermally for the purposes of environment protection. This is equivalent to 54% of all the waste of the city of Vienna.
About 60% thereof is burnt in Spittelau. During incineration, the waste delivers 60 megawatt of heat and, in addition, sufficient power to meet the needs of the plant itself.
In the district heating plant using natural gas and special fuel oil, 400 megawatt of heat can be produced.
The disposal of a city's waste is a problem. Space available in existing dumps is becoming scarce. If waste is dumped in untreated form, there is a risk of dangerous gases developing and of polluting underground water. Austria's new waste disposal law decrees that in future only a small proportion of refuse may be dumped untreated.
One solution is controlled, precisely managed incineration in combination with optimum flue-gas cleaning, following which only few and chemically inert residues remain over.
The pressure is heavy. Up to 250 refuse collection vehicles have to be handled every day in the Spittelau plant. They arrive with up to 1,200 tons of household refuse.
At 8 dumping points, these lorries empty the refuse into the storage pit. The storage pit has a capacity of 7,000 cubic meters. It is the storage base for the Spittelau plant because the furnaces are in operation around the clock.
Waste incineration is carried out in 3-shift operation. 2 gantry cranes, each fitted with a 4 cubic meter polyp grabber, cope with the piling work in the bin and feed the 2 furnaces.
The refuse lands on hydraulic distributors, which spread it out on 2-run reverse-acting grates.
Regarding incineration, all the technical possibilities are utilized to achieve a high temperature. This ensures that the amount of dangerous residue is kept to a minimum. The incineration is precision controlled by a power output calculator.
Through slits in the grate cover, 80,000 cubic meters of preheated air per hour are introduced. In addition, secondary air is force-blown by means of nozzles onto the front and back of the undergrate chamber. This means that the temperature in the combustion chamber above the grate goes up to 1,150 degrees Celsius.
During the unstable start-up and rundown phases, 2 gas burners guarantee a temperature of at least 800 degrees Celsius. The flue gases thus burn better to extinction, and the exhaust air remains clean.
Technical provision is also made in the Spittelau plant to ensure complete combustion of waste. A cyclical motion of every second grate rung slowly revolves the burning waste.
After incineration is completed, not much is left of the enormous piles of waste. Slag and ash only amount to 10% of the original volume.
At the end of the grate, a roller propels the burnt-out slag into the water-filled extractor.
On its way to the slag pit, a magnetic extractor separates all scrap from the slag. This is then recycled.
Slag and ashes no longer react chemically and therefore represent no danger to the underground water or atmosphere when dumped. They are bonded with water and cement into slag concrete and used for the construction of a concrete ring at the Rautenweg dump. This makes valuable savings in dumping volumes.
The heat from waste incineration, which takes place in 2 parallel lines, is used to best advantage by steam boilers.
The flue gases emerge from the combustion chamber at a temperature of 800 degrees Celsius. They flow through the second boiler pass with its contact evaporator, and in the third pass they warm the feed water up to boiler temperature.
The 2 boilers work on the natural circulation principle and have a heatable area of 2,400 square meters.
The natural circulation steam generator consists of a cylinder, the descending and ascending tubes, and the contact heating surfaces.
Together, the 2 waste boilers produce 90 tons of steam per hour, up to a pressure of 34 bar.
This pressure must be reduced before the water can be heated for the district heating network. It is utilized through a back pressure turbine to produce current. The attached generator can produce 6 megawatt of current. It supplies the power needs of the waste incineration plant and also feeds current into the public network.
After leaving the turbine, the steam is condensed in a heat exchanger group. This heats up the return water from the district heating network from 70 degrees to 155 degrees Celsius. The heat output is 60 megawatt.
In the district heating plant, in case of high heat demand, the output can be raised to 400 megawatt. For this purpose, there are 2 hot water radiation boilers, each rated at 170 megawatt, and 3 three-pass boilers, each rated at 20 megawatt.
The Spittelau district heating plant is located in a residential district of Vienna. That represents a challenge to environmental technology, but also to external appearances, because Spittelau is part of the municipal living space.
The Spittelau district heating plant is a fantastic demonstration of a successful symbiosis of art and technology. The painter Friedensreich Hundertwasser, a fantastic realist, undertook the outward enhancement. The result? A strictly functional building has been transformed into a unique work of art, a new Vienna landmark.
Hundertwasser is a dedicated campaigner for nature and environment protection. He was easily convinced of the desirability and absolute necessity of waste incineration. His facade design demonstrates his view of the dichotomy between technology and nature, a geometric chessboard opposed to natural, flowing, irregular forms.
The whole opus is crowned with a golden ball which houses an emission measuring station. Precise observations are made here of everything that emerges from the chimney. The golden ball symbolizes the importance attached by Fernwärmer Wien to pure air.
Measurements are taken of dust, sulfur dioxide, carbon monoxide, nitrogen oxide, hydrochloric acid, hydrocarbons, and also of heavy metals.
By means of a direct computer link, Municipal Department Number 22 monitors compliance with strict threshold values.
The Spittelau plant operates at an even higher degree of environmental efficiency than foreseen by law. Since 1994, the Viennese can check this for themselves. A display panel on the Lichtenwerderplatz shows the relative values in percentages. The permitted levels are generally never reached.
The Spittelau has an outstanding international reputation concerning air purifying and is regarded as exemplary environmental construction.
The expenditure involved in achieving such extremely low emission levels is high. In the Spittelau plant, electrofilters, flue-gas washers, and a denox plant have all been installed.
To start with, the flue gases must pass through electrofilters. These reduce dust from the extracted air from 5,000 to 5 milligrams per normal cubic meter.
That is to 1,000th of the original level.
For new plants, a maximum level of 15 milligrams per normal cubic meter is specified. The Spittelau does not even emit 1/15th of this amount.
The extracted dust is transported by screw conveyors to an intermediate silo, then filled into a silo transporter and sent for final conditioning to the Rautenweg dump.
The dust-less gases are fed into a flue gas washing plant. Spraying with fresh water reduces their temperature to 60 degrees Celsius.
Subsequently, they pass through the first washing tower. The pH value of the wash water is stabilized by the addition of lime slurry at a value of 1.
The extraction of hydrochloric and hydrofluoric acid, as well as of dust particles and heavy metals, is undertaken in sealed, double-hollow conical water shields.
In order to prevent the transfer of calcium ions from the first to the second scrubber, a mist eliminator has been installed between the two scrubbers. It contains interspersed lamellas on which the water drops which have been carried along will impact and be carried back to the first scrubber.
Sulfur dioxide is separated in the second scrubber. It is designed as counter-flow scrubber. The pH value is stabilized at around 7 with the soda lye and flowback water from the MR stage. The quantity in circulation amounts to approximately 900 cubic meters per hour.
After a further mist eliminator, the flue gases are fed into the electrodynamic venturi and then expanded in the diffuser. The fine dust particles form cores for small droplets which are separated in high-density water shields.
This measure is furthered by placing the middle electrodes in the Venturi nozzles under high tension. After passing through a further mist eliminator, the flue gas is warmed in a dryer before it reaches the induced draft fan.
Large quantities of water are required for flue gas washing. They are taken from the Danube Canal.
After the flue gas cleaning, the water is cleaned and after cooling and being given a final check, is fed back into the Danube Canal.
The wash water of flue gas scrubber number 1 contains chlorides, fluorides and heavy metals. It first passes through a heavy metal sink.
The resulting heavy metal hydroxides are bonded using iron 3 chloride and a polyelectrolyte and turned into flakes. Mercury and cadmium need an additional special precipitant. The separation is achieved in a lamella-type baffle plate thickener.
In the second precipitation stage, the fluorides are likewise sedimented in a lamella-type baffle plate thickener and passed on with the hydroxide sludge from the first precipitation stage to the filter presses. The dehydrated thin sludge forms the filter cake. So far, no way has been found of further processing it economically.
This unusable remainder, however, only constitutes 1/1000th of the original waste quantity. It is filled into big bags and used to pack galleries in the abandoned Heilbronn salt mine.
The wash water from the second scrubber contains sodium sulfate. It is put into the MR reactor.
By adding lime slurry, the pH value is raised from 7 to 10.5. Reprecipitation takes place with the formation of gypsum and the release of soda lye, which can be employed in the cycle of the second scrubber.
The gypsum is sedimented in the attached clarifier and pumped to the slag extractors of the refuse boiler.
For the last stage of the cleaning process, the flue gas from both boiler units is passed through the denox plant. At this point, the nitric oxide is cracked and the residual dioxin destroyed.
The Spittelau plant uses Europe's first catalytic converter, working on the principle of selective catalytic reduction, SCR for short, following waste incineration.
While entering the denox plant, the flue gas is sprayed with vaporized ammoniacal liquor.
A heat duct, which withdraws heat from the flue gas after the catalytic converter, raises the temperature in the crude gas to around 220 degrees Celsius, and a natural gas duct burner pushes it up further to 280 degrees Celsius.
When nitric oxide and ammonia react at this temperature, nitrogen and water vapor are formed. That is to say, natural constituents of the atmosphere.
The catalytic converter has the task of releasing this reaction.
The surface of the catalytic converter must be as large as possible in order that the nitric oxide can react for long enough to split up and the dioxin be destroyed. It consists of porous, ceramic, titanium, vanadium, tungsten briquettes.
In its 3,024 elements, there is a honeycomb of reaction surfaces available measuring 46,000 square meters. Microscopically fine pores enlarge this to 2.7 billion square meters. equivalent to 6.5 times the area of the whole city of Vienna.
The dioxin discharge from Spittelau is reduced by the catalytic converter by 99% and now stands at a dioxin equivalent of between 0.02 and 0.04 nanograms per normal cubic meter.
The legally permissible limit is 0.1 nanogram per normal cubic meter.
After passing through the catalytic converter, the flue gas is cooled in the heat duct and in an attached heat exchanger down to about 115 degrees Celsius.
The gas emerges from the chimney at a height of 126 meters.
The most modern handling and computer technology ensures smooth running of the whole Spittelau plant's operation. Control is exercised from a central command post. Processing computers here handle 9,000 items of incoming information every second and display the results continuously on control screens.
The combustion level, the washing plants, the wastewater treatment, the denox plant, the boilers and many other points can be controlled and managed from the central command post.
The measured values of emission are also continuously displayed and, together with many other data, stored for future reference.
From a second observation point, the network of the Fernwärme Wien is continuously monitored, controlled and adjusted.
It is Austria's largest district heating network. There was a modest beginning. Fernwärme Wien was founded in 1969. It then had a double task: incinerating waste and providing district heating.
Several existing heating plants and house units producing district heating were incorporated into the new company. In addition to supplying the General Hospital, Fernwärme Wien GmbH undertook the task of building up the Vienna district heating network.
Since then, the district heating network has grown to 700 kilometers and meets about 1/4 of the annual requirements for space heating in the federal capital. The heat is supplied by the two household waste incineration plants Spittelau and Flötzersteig, the dangerous waste incineration plant Simmering, and the thermal power compounds of Simmering Power Plant, of the Schwechat Refinery, and of the Leopoldau Gas Steam Turbine Power Plant.
And whenever these plants are unable to meet demand, peak performance boilers at the Arsenal, Kagran, Süd, and finally Spittelau are started up.
Only 4% of the heat supplied by Fernwärme Wien is produced from gas and oil.
Waste incineration and thermal power compounds save almost 300,000 tons of fuel oil every year in Vienna. By economizing on primary energy sources, 900,000 tons of carbon dioxide emissions are averted and the Vienna air situation greatly relieved.
However, that is not sufficient. 1/4 of all Vienna households still heat with fossil fuels and thereby cause 96% of total air pollution through space heating.
Increased use of district heating could ease this situation and reduce the size of the refuse piles. Exemplary technology ensures clean air.
The Spittelau district heating plant shows how this can be done.